Excited to share with you some of our research works on long context agents. I was told that we're in a very technical audience, so I guess you pretty heard about language models and agents. And long context is definitely one of the main challenges in agents. So imagine that you are doing agents to digest your emails, or you have data analysis files to have agents to process, or you have whatever particular jobs, you more or less encounter this long context problem. And there was this emerged practice in the community where we divide long context into chunks. And for each chunk, we have a separate agent to digest, and the responses of each agent will be aggregated to synthesize the final outputs. So the agents here could be local or cloud, depending on your applications. So our research question is, does it really work? And when it doesn't help? To understand this question, we come up with this very simple framework we call by divide-conquer agents. So for some long context documents, we divide into chunks, and we assign each worker to one chunk. The responses of each workers will be aggregated for a manager agent to come up with a final answer. And we have another planner agent who decides the job for each worker and manager agents. Just think of this task query. Well, we want to find what's the second smallest number among a long list of numbers. So the planner agent will understand this query and come up with a job to each worker to return the two smallest numbers instead of the second smallest numbers. So the two smallest numbers from each chunk will be sent to the manager agent so that the manager agent can decide what's the second smallest numbers globally. So it's a very simple framework, but it turns out to be work super well. We're able to be GPT-4 with simple models like 8B models, open source models in QA and many other tasks. In our paper, we come up with some theoretical framework to characterize the whole understanding thing into three types of noises: the modal noise, the task noise, and the aggregator noise. But I will leave the theory for now. But what's interesting about this noise is that we characterize three different scenarios where divide-conquer agents could help or not. The first scenario is where we find divide-conquer agents and the single agents perform approximately at the same level, which is like a KV retrieval. So you have a long KV pairs, which is like a dictionary. And you give this long dictionary to an agent and ask to find what's the value associated with this key. So this task is particularly good for divide-conquer, but the single agent now could perform as well. So we can see from this figure A that they are approximately at the same level. But then there is the second scenario where divide-conquer agents help a lot and outperform commercial closed source models, where we include the tasks like mathematics, question answering, and summarization. Note that for the divide-conquer agents, the models we use here are pretty small. So the cost for tokens is significantly lower than those commercial models. Because as you may know that if you call API for GPT models, you are counted by the tokens. When you are in long context, your tokens is significant. But also what's interesting is that we found this third scenario where divide-conquer agents doesn't help much. Here we have this figure F, which is the character inference. So we give a long dialogue script to agent, and it's a dialogue of multiple peoples. We mask one speaker out, and after we feed this long script to the agent, we ask the agent to infer who is the speaker's name. So it turns out that that's a very difficult task for divide-conquer agents because it requires cross-chunk understanding of your task. So that's a real long context task. So with these three scenarios, we have some great understanding and intuition about these divide-conquer agents. But the natural question is, how util can it be? What can we leverage it? It turns out we can come up with a very cheap estimation of the optimal chunk size with simple, like a 5-sample, 10-sample estimation. With only like a few samples, we are able to come up with an optimality closer to the exhaustive search. So just imagine if you are in a product deployed, you can estimate some queries with single hyperparameter easily that you can solve the user's query in a very cheap way. So it's actually very easy to productize. This product has been also used this algorithm has been also implemented in some open source projects like AutoCAD AI's Open Deep Research, where you send a query and we search a lot of web pages, and each web page is summarized by separate agents. So it's in parallel, so it's fast. And also it performs well. The summary of each agent is aggregated towards the final aggregator agent. So there's also an interesting scenario where your worker agent outputs a very long response. So this way, if you aggregate the responses of your agents, it's still a long context problem, right, for your manager agent. So naturally, you probably want to do it multiple rounds to squeeze, squeeze, and squeezer. So let's say we have 3 rounds of divide conquer here. There's one thing we didn't mention much previously, is that about the time. So if you do it divide conquer multiple times, you actually, the time to get your final synthesized output is super long, and that's not tolerable in a product. This can be easily characterized by this figure. So let's say we have proposal 1, 2, 3, which is agents, worker agents in one layer, and then we have the aggregator. So traditionally, we have to wait until all worker agents to finish before we can produce something meaningful. Wait until full responses are available. Then we start to aggregate answers and feed this to the aggregator agents to generate something. But that's too slow, and we want to come up with something clever. So we still do the chunk for the output of each proposal's response. So proposal, basically, they stream their response in chunks. The chunk size could be a predefined thing. And the aggregator agent will now instead aggregate the chunks for all the proposals. Then it starts to chunk its own output as well. So by comparison, we use the metric here called TTFT, time to first token, which is like a commonly used metric in products of language models. And we show that with this mechanism implemented, we can reduce token to fast time by time to first token by 93%, which is a huge improvement. Yeah, so with that said, if you are interested in more details, I invite you to check out 2 papers. It's a joint work with Stanford DeepMind together in Duke. I'm happy to take questions. Thank you.
So you mentioned the problem with semantic versus partitioning. So you might accidentally split the semantic into 2 different chunks, and now you have 2 agents looking at something. Did you address that? How did you solve it?
So we asked the planner to handle these semantic jobs. So whatever query we use to, we want from the whatever benchmark or user's query, we ask the planner to digest. We ask the planner that we tell the planner explicitly we're doing this divide conquer thing, and we ask the planner to assign the prompts for our workers and the manager agents. So the planner handles all this semantics complexity. Let me give another example. Let's say we're doing a multiple choice query, and we have a question, we have multiple choices. So if the planner sees that there are, say, the question could be, what's the color of these jeans? And there are multiple colors as options. So the planner agent sees these options. So they will use these options as part of their queries for workers. For example, if they were asked that, can you find something that's black, or can you find something that's about jeans? So these are part of the semantics divide conquer that's assigned to different agents.
So my question is, I think there are 2 types of the deep search agents. One is more like a recursive approach, and the other one is more like a iterative approach.
Yeah.
So for a recursive approach, it's like you divide the conquer, and then on the second layer, you can also have another divide and conquer. So I was wondering, for your research, are you doing these into multiple layers, or do you constrain or limit the number of layers to a fixed number, like 2 or 1?
I think it's a product choice. Both paths are not conflictive. You can implement both at the same time, and it's your product design choice. How many rounds you want to limit for, how many rounds of divide conquer you want to limit for digesting this batch of query, and how many times of loop you want to loop in, because you will have a manager agent to decide, okay, did we finish the user's job well? or do we want to continue searching? So there is also this loop decision. So that's I think that's a design choice depending on your applications.
Cool. A second question is like compare the performance of a GPT-4o with many like smaller language model course. But those models are actually pretty old, in today's standard. Have you tried to compare the performance of like more recent like small language models versus let's say GPT-5 or some other like flagship models?
Yes, so we do compare with some Gemini models, and still, we think this divide conquer phenomenon exists, and the three scenarios could exist. But the performance gain is like depending on what exact model you choose, and also even the commercial models are better and better. The open source models is also better and better. Also because of this MOE architecture, the cost is not that high compared to those Llama 70B models. So it's interesting to bench them again, but depending on what you want to compare, I think there is still the space for this like Pareto or economics benefits comparing commercial models with open source divide conquer agents.
Thank you.